It is incredibly easy to look at a massive hyper-intelligent language model today and just think of it like this sci-fi supercomputer.
Oh, absolutely. It totally feels that way.
Right, like you type in a really complex question about, I don't know, quantum physics or like 17th century poetry, and it talks back this brilliant, perfectly articulated answer in seconds.
Yeah, and honestly, it feels like magic.
It really does. But the reality is, if you pull back the curtain and really look under the hood of a raw language model, it's less like an all-knowing digital god and more like a super genius locked in a windowless room with an encyclopedia from 2 years ago.
That analogy, I love that because it hits the nail on the head. It really highlights the tragedy of raw capability versus actual utility.
The tragedy of it. Yeah, explain that.
Well, this entity has all this latent intelligence, right?
Mm.
Billions upon billions of parameters of encoded knowledge, but it is completely trapped inside its own architecture. I mean, it can think, but it can't touch.
And that profound limitation is exactly what we are unpacking today. So welcome to the deep dive. We are looking at a massive fundamental shift in technology right now.
A huge shift.
Yeah. For anyone listening to this who has used a basic AI chat tool and thought, okay, this is really cool. It can write a poem or summarize a long email thread, but how does it actually, do things in the real world?
Mm-hmm.
This deep dive is your ultimate blueprint.
It really is.
We are deconstructing something called LangChain. But we're not just looking at it as a piece of software or a coding library. We are going to examine it as the orchestration engine.
Right, the crucial bridge between those raw, isolated language models and truly autonomous, independent applications.
Exactly.
LangChain really is the missing link in the modern AI stack. I mean, the core premise we need to establish for you, the listener, right out of the gate, is that right now, large language models, or LLMs, are incredibly smart, but they're entirely isolated.
They're stuck.
They are quite literally brains in jars. So the goal of our conversation today is to explore exactly how orchestration breaks the glass of that jar.
Breaking the glass. I love that visual.
Yeah, it is the system that gives these isolated brains hands to manipulate their environment. It gives them memories to recall past interactions with you and the ability to dynamically navigate the incredibly messy, unpredictable real world.
So here is the journey we are going to take you on today. We have to start by diagnosing this core problem of the isolated AI. Like, what does it actually mean technically and practically to be a brain in a jar?
Right, we have to start there.
From there, we will explore the foundational building blocks of the solution, the master blueprint of orchestration. And once we have that architecture down, we have to figure out how to feed this brain real-world data.
Which is a massive hurdle on its own.
Oh, absolutely. We'll look at how to give it a functioning, reliable memory, and finally, the really exciting part, we're going to watch it come alive as a fully autonomous agent capable of making its own decisions.
It is a phenomenal progression to witness. You are watching the evolution from a static text generator to a dynamic digital actor. And honestly, understanding the mechanics behind it changes how you view the entire technology landscape.
Let's start by diagnosing the patient. The fundamental problem of an isolated LLM can be boiled down to three very specific, very clinical terms.
Okay.
If you just grab a raw model off a server, it is stateless, it is read-only, and it is disconnected.
Yes.
These aren't just buzzwords, right? They are crippling limitations. So let's break those down, because understanding them is crucial to understanding why we need an orchestration layer in the first place.
They absolutely are the hurdles that every developer hits on day one. These three limitations are the exact reason why you cannot just plug a raw AI model into your business operations and expect it to run things.
Right. So let's look at the first one. Stateless.
Yeah, so in computer science, being stateless means having absolutely no memory of past interactions.
Not at all.
None. The system does not retain any state from one moment to the next. When you talk to a raw LLM, every single prompt you send is the first time it has ever met you.
So it essentially has a goldfish memory.
It has a goldfish memory.
So if I type into a raw model, my name is John, and I love hiking, it will say, nice to meet you, John. But if I clear the screen and at the very next prompt ask, what is my name and what should I do this weekend? A truly stateless model has absolutely no idea.
Precisely. It doesn't retain the context from interaction A to interaction B. The neural network itself, it doesn't update its weights based on your casual conversation.
It's fixed.
Exactly. Every input is processed in a total vacuum. If you are trying to build any complex application that requires a back-and-forth diagnostic, say, a customer service bot trying to troubleshoot a broken router statelessness is a complete deal breaker.
Because the bot would ask for your account number every single time you reply.
Exactly. Every single time.
Which is incredibly frustrating and entirely useless for real-world tasks. Okay, so what about the second limitation, read-only?
So read-only means the model cannot take real-world action. Let's say you want an AI to book a flight for you.
Okay.
A raw LLM can generate brilliant text about booking a flight. It can give you a list of airlines. It can tell you the best time of year to fly. It can even write the exact Python code required to interface with Delta's API.
But it can't actually do it.
It cannot press the button. It cannot send the HTTP request, and it certainly cannot pull the funds from your bank account to finalize the transaction. It can only read its internal neural weights and spit out text. It has no hands.
Wow. So it's all theory, no practice. I mean, it can tell you how to defuse a bomb, but it can't hold the wire cutters.
That is a very vivid but very accurate way to put it. And that leads directly into the third limitation, which is being disconnected.
Disconnected from the real world.
Right. This means the model has zero access to outside real-time knowledge. Its entire knowledge base is frozen in amber at the exact moment its training data was cut off.
So if it was trained 2 years ago, it only knows things up to 2 years ago.
Exactly. If you are using a model trained up until December of last year, and you ask it for today's weather in Chicago, or the current stock price of Apple, or most importantly for a business, the status of an internal database updated 5 minutes ago, it is completely blind.
Going back to my super genius in the windowless room analogy, this paints a really clear picture. They know a massive amount of information up to a certain date. But they don't know who you are because they are stateless.
Right.
They can't pull a lever to open the door because they are read-only. And they can't browse the web to find out what happened in the news this morning because they are disconnected.
That is the exact, unvarnished diagnostic reality of a raw LLM. And this is precisely where LangChain enters the picture to completely rewire the paradigm.
So how does it fix it?
LangChain's solution is the orchestration layer. If you imagine a computer, the LLM is just the central processing unit, the CPU. It's powerful, but it's useless on its own. LangChain is the motherboard that surrounds it.
Okay, I like that. The motherboard.
Yeah, it plugs in external knowledge API, so the AI is no longer disconnected. It plugs in functional tools, so the AI is no longer read-only. And it plugs in memory banks, so the AI is no longer stateless.
It takes the isolated brain and wires it into a central nervous system.
Yes.
And for the listener, it's really vital to understand that this isn't just theoretical computer science happening in an academic lab somewhere. The industry adoption footprint for this orchestration architecture is staggering.
It's massive.
We are looking at over 15 million monthly downloads, and it is currently powering over 100,000 live applications. This is the invisible infrastructure of the modern AI boom.
And it is being deployed at the absolute highest levels of enterprise, where the stakes are incredibly high. There's a specific use case that I think perfectly illustrates why orchestration is so vital, beyond just making, cool chatbots.
What's the example?
Take Ally Financial. They use LangChain modules specifically to mask personal identifiable information PII in a compliant manner.
I want to pause on this, because on the surface, masking data sounds a bit dry, maybe even a little boring compared to the sci-fi dream of an AI booking your vacation or writing your code.
Mm-hmm.
Why is this specific Ally Financial example the linchpin for understanding enterprise orchestration?
It might sound dry, but data security is the entire ballgame for enterprise AI adoption.
It's everything.
This example proves that orchestration isn't just an experimental toy. It's a mission-critical, enterprise-grade filter. Think about the reality of a massive institution like Ally Financial. They have mountains of data. They desperately want to use the incredible reasoning power of large language models to analyze messy customer service transcripts or evaluate complex loan applications or detect fraud patterns.
But they can't just hand that over.
Exactly. They face a massive wall. They absolutely cannot send raw, unencrypted customer data like social security numbers, home addresses, account balances to a third-party AI provider like OpenAI or Anthropic.
Because the moment that prompt leaves their internal servers and goes out over the internet to a third-party API, it's a massive compliance violation. You're breaching GDPR, CCPA, and basically every financial regulation on the books.
It would be a catastrophic breach.
Yeah.
But how do they solve this without abandoning AI entirely? They use LangChain as a protective orchestration layer.
How does that work in practice?
They build a pipeline. Before the employee's prompt or the customer transcript ever hits the actual LLM brain, it passes through a specific LangChain module designed to act as a security guard.
Oh, wow.
Yeah, this module uses pattern recognition to detect and scrub PII. It replaces real names with dummy names, it redacts the social security numbers, it obfuscates the account details.
Then and only then, it sends that clean, sanitized prompt out to the external LLM.
Correct. So the external LLM does its complex reasoning. Maybe it determines the customer in the transcript is highly frustrated and qualifies for a fee waiver. It sends that reasoning back. But the user looking at the screen internally needs to know which customer this applies to, right?
Right, a fee waiver for dummy name A isn't very helpful.
Exactly. So the orchestration layer receives the clean answer and re-injects the real secure context back into the text before delivering it to the internal dashboard.
That is brilliant. It's a traffic cop, a security guard, and a translator all rolled into one.
It is.
Orchestration isn't just about giving the AI the power to do things. It's equally about controlling and constraining how data flows in and out of the model to ensure safety, security, and compliance.
It creates a deterministic wrapper around a probabilistic engine. It makes AI safe for business.
Okay, so we know why we need to rescue the AI from its isolated box, and we know why massive businesses are relying on this layer to do it safely. But how exactly do we build this? If you are a developer or just someone trying to understand the mechanics, what does the blueprint look like?
Well, to build it, you have to embrace a modular ecosystem. You have to break the problem down into distinct, manageable, structural pillars.
Let's walk through that master blueprint. The architecture of this orchestration layer is built on 4 distinct pillars. Pillar 1 is the brain. These are the models themselves.
Right. This is the core computational engine. And the beauty of a modular system like LangChain is that it is completely agnostic to the brain. You can swap the brain out like a light bulb.
Really, just plug and play.
Pretty much. Today, you might plug in ChatOpenAI because it's the smartest model available for your task. Tomorrow, Anthropic might release something better, and you just swap the API key.
That's incredibly flexible.
Or, if you have extreme privacy concerns, you might swap in an open source model running locally on your own private servers. LangChain just provides the universal socket. The brain's only job in this pillar is to evaluate the inputs it receives from the socket and generate raw textual responses based on its training.
Which brings us to Pillar 2, which shapes those inputs. Pillar 2 is the instructions. This covers prompts and parsers. This is all about formatting the inputs going in and rigidly structuring the outputs coming out. And I want to dive really deep into this one because this is where the actual engineering happens.
It is the most critical translation layer in the entire stack. This is where human intent is translated into machine instruction.
Let's look at the input side first. We are talking about something called a chat prompt template. It acts as a dynamic schema. The key concept here is that developers building these applications do not hard-code prompts. They use placeholder variables. Can you explain how this template actually functions in a live application?
Think of a chat prompt template like a high-tech, automated fill-in-the-blank form. When you are just playing around with a chatbot on your laptop, you might type out the whole sentence like, write a brief 2-paragraph definition of blockchain technology.
Right.
That is a hard-coded prompt. You, the human, did all the assembly work. But in an enterprise application, you are processing thousands of requests from users automatically. You can't have a human manually typing the prompt every time a user clicks a button on your website.
Right, the application itself needs to dynamically generate the prompt based on user behavior.
Exactly. So a developer creates a base template box. The template might be coded to say, write a brief 2-paragraph definition of technology name. Use a professional tone suitable for an executive summary.
And the curly brackets around technology name, that turns that phrase into a dynamic placeholder variable.
Yes. Now, imagine a user is navigating your educational app. They click a button that says quantum computing. The application doesn't ask them to write a prompt. It simply takes the variable quantum computing, passes it into the template, snaps that phrase into the empty slot, compiles the final pristine instruction string, and fires it into the LLM engine.
It's an industrial assembly line. You have a standardized, perfectly engineered frame, and you are just dropping the custom part into the slot as it rolls down the conveyor belt.
That's a great way to picture it. It ensures absolute consistency. The LLM always receives the instruction in the exact same format, which drastically reduces errors and hallucinations.
So that handles the input. We've standardized how we talk to the brain. But the output side of Pillar 2 is where things get really fascinating and, frankly, a bit contentious. Because once the LLM gets that perfectly formatted prompt, it is going to generate a response in natural human language.
Mm.
And human language, by its very nature, is messy.
Oh, extremely messy. Which brings us to output parsers. This is the process of enforcing chaos into data.
Let's look at a concrete example. Say we have unstructured input messy text from an LLM that says something like, wow, the new phone is absolutely great. The battery life is stellar. I give it 5 stars out of 5. Highly recommend it to anyone.
Right, a very standard human-sounding review.
Exactly.
Yeah.
If we push that through a filter called a JSON output parser, using something called a pedantic schema, the result is this strict, sterile, structured output. It just says product name, dot phone, rating, 5.
This is one of the most underappreciated miracles of orchestration. It is the bridge between AI and traditional software.
Okay, I have to push back on this, though.
Yeah.
I am going to play devil's advocate for the listener who is scratching their head right now.
Go for it.
Because the whole point of large language models, the entire reason the tech industry has spent billions of dollars and unimaginable amounts of electricity on them, is that they understand and generate natural language. They speak like we do.
They do.
So why, when we finally have a machine that can talk in beautiful, nuanced human text, do we immediately force that messy human text back into a rigid, cold JSON format? Aren't we working backwards? We taught a computer to speak English, and now we are forcing it to speak in curly brackets and colons again.
It is a fantastic question, and it really gets to the heart of the friction between AI and traditional engineering. You are absolutely right that human language is beautiful, nuanced, and expressive. It is incredible for chatting with a user, but human language is absolutely toxic for software logic.
How so? Break that down.
Think about the downstream application that has to receive this data. Imagine you have built an automated customer service pipeline. A user submits a long, rambling review on your website. You use an LLM to read it, analyze the sentiment, and extract the key data points.
Okay.
The LLM correctly decides it's a glowing review of your new phone. But the LLM is just step one. The next step in your pipeline is an inventory database that needs to update the product's average rating and maybe a marketing dashboard that tracks positive mentions.
Right.
That database is written in traditional SQL or maybe Python. It is expecting an integer. It is expecting the mathematical number 5.
It's not expecting a conversation.
Exactly. If the LLM sends that SQL database a conversational string that says, wow, I really love this, it's a solid 5 out of 5 stars, the database will instantly crash.
Really? Just from that?
Yes, it doesn't know how to multiply, average, or index a sentence. It needs a structured number in a specific column. Traditional software is deterministic. It operates on strict rules, strict types, and strict schemas. Large language models are probabilistic. They operate on chance, context, and language prediction.
So they basically speak two fundamentally incompatible languages.
Yes, they do. Parsers are the vital translation layer between human unpredictability and machine strictness. When you use a pedantic schema, which is a data validation library in Python, you are essentially drawing a rigid box.
Okay.
You are telling the parser, I don't care how chatty the LLM was, I don't care if it wrote a sonnet about the phone, look at the text, extract the name of the product as a string of text, extract the rating as a whole number integer, throw away all the conversational fluff, and hand me a pristine JSON object that my database can actually read.
You are literally enforcing chaos into data. You squeeze the meaning out of the chat and discard the rest so the rest of your software stack doesn't break.
And LangChain ties this entire input-output lifecycle together natively, using something called LCEL, the LangChain expression language.
Let's unpack LCEL. It's described as a declarative pipeline that natively chains these components together, so the output of one block automatically formats as the input for the next. The sequence is prompt block, then LLM block, then parser block. How does this actually look in practice?
Think of LCEL as the industrial plumbing of your application.
Plumbing.
Yeah. Before LCEL existed, developers had to write lots of messy, custom imperative code to manually grab the output from the template, format it correctly, send it over the network to the LLM, catch the asynchronous response, handle errors, and then feed that raw text into the parser.
Sounds exhausting.
It was. LCEL simplifies this radically. It allows developers to literally use a pipe operator, the vertical bar on your keyboard, which comes from Unix philosophy, to connect these distinct modules. You define your prompt template, you pipe it to your model, and you pipe that to your output parser. The data flows through that pipeline automatically, handling all the complex asynchronous routing in the background.
So the prompt block structures the chaotic user input, hands it cleanly to the LLM block, which generates the raw probabilistic reasoning, and that raw response flows directly into the parser block, which enforces the deterministic JSON format. It really is an industrial assembly line for thought.
It is, and it allows developers to create incredibly robust, error-resistant applications out of underlying AI models that are inherently unpredictable. You are building a reliable machine out of unreliable parts.
Okay, so we've got pillar one, the brain. We have pillar two, the instructions and parsers. We have structured how we talk to it and how it talks back to our software. But here is the gaping hole in our architecture. If I ask this tightly orchestrated, perfectly formatted brain a question about my company's specific internal HR policy from a PDF I wrote yesterday, it is going to fail miserably, right?
It will completely fail, yes.
Because, going back to our initial diagnosis, it is still completely disconnected from my specific reality.
Exactly. The prompt is perfect, the parser is waiting, but the brain only knows what it was trained on months or years ago. To make it truly smart about your specific problems, your private company data, we have to feed it the world.
Which brings us to pillar three, the context.
Right.
Specifically, feeding the brain through ingestion and the fine art of semantic chunking. How does LangChain actually ingest external reality? We're introduced here to the data preparation matrix. These are the primary tools used in what the industry calls a RAG pipeline.
Let's define RAG quickly for the listener. That stands for Retrieval Augmented Generation. It's an incredibly powerful concept. Instead of trying to fine-tune an entire model on your company data, which is wildly expensive and difficult, you retrieve relevant external data from your databases and you augment the AI's prompt with that data before it generates an answer.
It's like giving the student an open book test instead of making them memorize the textbook.
Perfect analogy.
Got it. So the first half of this data preparation matrix consists of document loaders. Their primary role is ingestion converting messy real-world files like external APIs, PDFs, Word documents, and massive CSV spreadsheets into usable, standardized document objects that the system can understand.
Right.
And the critical feature we need to highlight here is lazy loading. This is the ability to pull data only when necessary to optimize memory usage. The classic example is a CSV loader, loading a massive database and tagging columns as metadata. Why is lazy loading so crucial here? Why not just grab the whole PDF or spreadsheet and dump it into the model so it has all the context?
Well, you can't just dump it in for two major reasons: system memory limits and AI memory limits. Let's look at system memory first. Imagine you are a major retailer and you have a CSV file with 5 million rows of historical customer purchase data.
That's a huge file.
If your LangChain application tries to load that entire file into your server's active RAM all at once to process it, it will cause a memory overflow and crash your server instantly. Lazy loading is a sophisticated technique where the document loader reads the file packet by packet, row by row, processing it as a stream as needed rather than swallowing it whole.
So it protects your physical hardware.
Yes. But even more importantly, it protects the AI. You absolutely cannot dump a 5 million row CSV or a 500-page PDF directly into an LLM's prompt box.
Because the prompt box isn't infinitely big.
Right. Every LLM has a strict token limit, which we call the context window. A token is roughly equivalent to a word or a word fragment. If a model has a token limit of 8,000 and you try to shove a 50,000 word corporate manual into the prompt, the model will just throw a hard error. It refuses to process it.
It's like trying to force a fire hose through a garden hose.
Exactly. So you have to break your massive external documents down into smaller, bite-sized pieces before you can retrieve them.
And that leads us perfectly into the second half of the data preparation matrix. Text splitters. If loaders are ingestion, splitters are digestion. Their primary role is breaking massive documents into smaller chunks to fit neatly inside those strict context windows. But this is where the engineering gets really delicate, because how you cut the data matters immensely to the AI's ability to understand it later.
Oh, it matters more than almost anything else.
Let's explore the difference between a bad cut and a good cut.
This is arguably one of the most common fundamental mistakes developers make when they first start building RAG systems. They get the data in, but they slice it wrong, and the AI appears stupid.
Let's talk about the bad approach first. A bad cut is essentially a blind character count. A developer writes a script that just slices the document at an arbitrary number of characters, say every 1,000 characters, regardless of what is happening in the text.
Think about it from the AI's perspective. If you tell a script to blindly cut a string of text every 1,000 characters, it doesn't care about grammar, it doesn't care about paragraphs, and it certainly doesn't care about semantic meaning.
It's like trying to read a novel where someone has randomly run the book through a paper shredder every 500 words.
Yes.
Imagine you were reading this intense emotional scene or a highly technical legal contract. And right in the middle of a critical piece of dialogue or right in the middle of a clause explaining a liability waiver, the page just ends.
It just cuts off.
The sentence is severed in half. The rest of the clause is on a completely different piece of paper that might get stored somewhere else. It might not even get retrieved when the AI searches for it.
That is a perfect visualization of what happens. And you have to remember, LLMs rely entirely on context to reason. If an AI receives a fragmented sentence or a paragraph that is missing its introductory topic sentence because it was sliced off by a blind character count, its reasoning degrades drastically.
Because it doesn't have the whole picture.
Exactly. It starts hallucinating to fill in the blanks, or it just defaults to saying, I don't know, because the puzzle piece it received is literally broken.
So what is the alternative? How do we fix the shredder? The sophisticated approach is called semantic chunking. And to explain this, let's look at a specific tool called the HTML header text splitter. This tool doesn't cut blindly. It splits data logically at H1 or H2 HTML tags to preserve contextual meaning. And crucially, it attaches metadata to those chunks. Walk us through how this preserves the AI's sanity.
Semantic chunking is a total game changer. Instead of cutting blindly at 1,000 characters, the semantic splitter actually looks at the structural anatomy of the document. If it's ingesting a web page, an internal wiki, or a formatted manual, it looks for the natural joints, the chapters, the main headings, the subheadings.
It's cleanly separating the book by chapters instead of running it through a shredder.
Exactly. Let's say the HTML header text splitter is reading your company handbook. It sees an H1 tag that says employee leave policy. It says, okay, everything below this tag until I hit the next H1 tag belongs together. They share a semantic theme.
Makes sense.
It chunks that entire section as one cohesive block, respecting the natural flow of the concepts. And then it does something brilliant. It takes that H1 heading and attaches it as a persistent metadata tag to that specific block of text.
So the block of text has a digital sticky note permanently attached to it that says, this chunk is specifically from the employee leave policy section.
Yes. And the reason the metadata is so vital is that it acts as a permanent breadcrumb trail for the AI. Imagine you have a massive corporate database with tens of thousands of pages.
Okay.
The user asks a question, the system searches the database, and it retrieves a small chunk of text that simply says, employees are entitled to 2 weeks of paid time off. Without metadata, the LLM just sees that isolated sentence. It doesn't know if that rule applies to executives, part-time workers, international contractors, or interns.
The context is completely lost in the vastness of the database.
But with semantic chunking, that metadata travels with the text into the prompt. The LLM sees the rule, and it also sees the sticky note that says metadata context. Header 1, part-time employees. Header 2, paid time off. Suddenly, it has perfect crystalline context.
Oh, wow.
Yeah, it can confidently tell the user, if you're a part-time employee, you get 2 weeks.
It knows exactly where in the massive universe of corporate data this specific rule came from.
Yeah.
That is incredible. Okay, so we've solved ingestion. Now our AI can read and understand massive external documents without losing context because we are feeding it perfectly sized, logically grouped, heavily tagged chunks of data.
We fix the brain in a jar.
Mostly.
Bruh.
But wait, let's trace a real conversation. Let's say I ask the AI about that specific part-time leave policy, and it retrieves the chunk, and it answers perfectly. Great. But then I ask a casual follow-up question. Wait, does that apply to sick days too? How does it know what that refers to? If we go back to our initial diagnosis, we established as a hard rule that LLMs are inherently stateless. They have goldfish memory. So technically, the moment I hit enter on does that apply to sick days too, shouldn't it have completely forgotten that we were just talking about part-time leave policies?
Based on the raw architecture, it absolutely should have forgotten. It should look at the word that and have no idea how to resolve it.
Yeah.
And this brings us to one of the most fascinating aspects of orchestration, the illusion.
Let's dive into statefulness, the illusion of memory. We know LLMs are stateless. So how in the world are we having fluid, continuous, hour-long conversations with them on our phones every day?
Right.
The framework introduces a module called conversation buffer memory. And the key phrase here is that it creates the illusion of memory by maintaining a continuous log of actions and dynamically injecting it. Break this down for us. Why do you use the word illusion?
I use the word illusion, and we must stress this to the listener because it's important to understand that the LLM itself is not learning or remembering anything during your chat.
It's not.
No, its internal neural network, its actual weights and biases are not changing. It is not forming a memory the way a human brain forms a memory when you have a conversation.
So what is actually happening behind the scenes to make it feel so real?
It is essentially a parlor trick. A very sophisticated, computationally expensive parlor trick orchestrated by LangChain. What conversation buffer memory does is it acts like a silent stenographer sitting in the room.
A stenographer.
Yeah, every time you type a prompt and every time the AI generates a reply, the memory module writes both sides of the exchange down in a continuous running text transcript.
Okay, I'm with you.
When you ask your next follow-up question, does that apply to sick days too? End quote. The LangChain system intercepts it. It doesn't just send your new isolated question to the LLM. It takes the entire stenographer's transcript of everything you have both said up to that point, staples your brand new question to the very bottom of it, and forces the LLM to speed read the entire history of the conversation all over again from scratch before it generates its next answer.
So it's not remembering. It is constantly, frantically rereading the transcript of the conversation in real time every single turn.
Exactly. Every single time you hit enter, it reads the whole script again to figure out what that means. The architecture actually breaks down the three distinct streams of data that feed into the chat prompt template before hitting the LLM to make this happen.
Let's look at those streams because they build the context. First, there is the system message. This is defined as the persistent, unmoving context. For example, you are a helpful career coach who specializes in the tech industry.
Right. This is the overarching persona or the fundamental rule set. It never changes. It is the anchor at the very top of the prompt that dictates the tone and constraints of every interaction.
Second, there is the chat history buffer. This is the dynamic log we just talked about. It takes all the previous outputs and loops them back as input.
That's the stenographer's transcript sitting right below the system message.
And third, the human input. This is a current, immediate user prompt, like, what should I focus on next? So these three streams, the permanent rules, the running history, and the new question, all merge together on the LCEL conveyor belt, feed into the prompt template, and get shoved into the LLM at once.
Yeah, that is the complete anatomy of AI memory.
But wait a minute. Think about what that implies. If we are just constantly appending the entire history of the chat into the prompt over and over again every single time we speak, doesn't that transcript eventually get massive?
It does.
If I chat with a bot for an hour, don't we eventually hit that exact same token limit wall we just talked about with the massive CSV files and the text splitters?
Yes, absolutely. You have hit on the fundamental physical limitation of this architecture. If you talk to an AI long enough using a basic, naive buffer memory, the transcript will inevitably grow until it exceeds the token limit of the model.
And what happens then?
When it does, the model will just crash and throw a context window exceeded error right in the middle of your conversation.
Oh, man. So how do enterprise applications fix that? You can't have a customer service bot just lose its memory and crash in the middle of a complex refund process.
This is where LangChain's orchestration goes from basic plumbing to advanced engineering. Conversation buffer memory is just the simplest entry-level version. LangChain has a whole suite of advanced memory modules designed specifically to solve this exact problem.
Like what?
For example, they have something called window memory. This module acts like a sliding window. It only keeps the last, say, 5 exchanges in the transcript and automatically drops the older ones off the back.
Like a sliding window of short-term memory. But what if a detail from the very beginning of the chat was important?
Then you use an even more elegant solution, summary memory. This is brilliant. In the background, asynchronously, LangChain will periodically use the LLM itself to read the long, sprawling transcript and write a highly concise summary of the key facts discussed so far.
Wait, really? It summarizes its own conversation?
Yes. It then deletes the massive raw transcript and replaces it with this dense, short summary block, creating up thousands of tokens while preserving the core facts of the relationship.
Oh, that is incredibly clever. So the system is constantly compressing its own memories to save space in its limited brain capacity.
Exactly. And managing that compression, deciding exactly when to summarize, what details to keep, and how to format the summary requires immense computational orchestration. That is, the heavy lifting LangChain is doing invisibly in the background. The human user just feels like they are chatting naturally with a persistent entity that remembers them.
That is fascinating. Okay, let's take a breath and look at where we are. Up to this point in our journey, we have built a highly capable, well-read, structurally rigid, memory-retaining chatbot. It knows our private data through RAG, it remembers our ongoing chat through memory buffers, and it outputs perfect JSON for our databases through parsers.
It's quite a machine already.
It is, but a chatbot, no matter how advanced, just talks. It answers questions. It generates text. It doesn't actually do things independently. If we want to move beyond chatting, it's time to build something that acts. It's time for the paradigm shift.
This is the frontier. This is where we move from software that is merely highly intelligent to software that is functionally autonomous.
Let's explore this paradigm shift. From rigid chains to autonomous agents. The architecture defines this as the most fundamental leap in modern AI. We are moving from chains to agents. Let's define the baseline first so we understand the leap. What exactly is a chain?
A chain is essentially everything we've been talking about up until now. It is fixed execution. A great visual analogy to use here is a train on a track.
Right, the sequence is completely hard-coded. The prompt goes to the model goes to the parser goes to the database.
Exactly. In a chain, the human developer has laid down the steel tracks. The developer explicitly defined the logic. First, do step A, then do step B, then do step C. The LLM is just the engine pushing the train forward along those pre-laid tracks.
Got it.
But think about the limitation here. If there's an unexpected obstacle on the track, let's say an external API is down, or the user asks a highly ambiguous question that requires a step the developer didn't anticipate when they wrote the code, the train stops.
It derails.
It crashes. It throws an error. It cannot adapt because it is physically locked to the fixed execution path.
It is entirely rigid. It only succeeds if the world behaves exactly as the developer predicted. But an agent is completely different. The architecture describes an agent as dynamic routing, and the perfect counter analogy is a drone in a maze.
This is the paradigm shift that changes software forever. With an agent, you don't lay tracks. You give the drone a map, you give it a toolkit, and you give it a final goal. Then you drop it in the maze.
Okay.
The profound difference here is that the agent uses the LLM not just to generate text for the user, but as its own internal reasoning engine to decide its own control flow.
It observes its surroundings, it selects tools based on the current context, it adapts to unexpected obstacles, and it finds its own unique way to the exit.
It creates its own path on the fly. If tool A fails, it reasons, okay, tool A is down, I will try tool B.
Let's break down the anatomy of this drone. The framework outlines the anatomy of a LangChain agent into 4 distinct pillars. Pillar 1 is the agent itself. This is the core decision-making logic, using the LLM to analyze the context to determine the next action.
Think of this as the brain of the drone, evaluating the telemetry.
Pillar 2, tools. These are the external functions it can invoke at will. A web search API, an internal SQL database, a math calculator, a Python code execution environment.
These are the drone's physical attachments: the drill, the camera, the infrared scanner.
Pillar 3, and this one I find absolutely incredible, is called intermediate steps. This is the internal scratchpad. It's a continuous history log of agent actions designed specifically to prevent the AI from looping or duplicating work.
This scratchpad is vital for true autonomy. You cannot have an agent without it.
I really want to marvel at this concept of the scratchpad. It's like giving the AI a piece of scrap paper to show its work to itself before giving the final answer to the user. Like in an advanced math class, the teacher doesn't just want the final answer. They want to see the steps. Yeah. But here, the AI is doing it for its own sanity. It is keeping track of its own tactical failures and successes in real time.
And it absolutely has to, because if a drone flies down a hallway in a maze and hits a brick wall, it needs a way to remember, I already tried hallway B, it's blocked, do not try it again.
Right.
Without this intermediate step scratchpad, an AI agent will often get stuck in an infinite catastrophic loop. It will constantly try to query the same failing tool over and over and over because it literally forgets that it just tried it a millisecond ago.
So the scratchpad is its short-term tactical working memory, completely separate from the conversational memory we discussed earlier.
Exactly. It's the memory of its own actions. And once it navigates the maze using that scratchpad, we reach pillar 4, Agent finish. This is the terminal state where the agent decides the goal is met and the final structured output is delivered back to the user.
The drone successfully navigated the maze, found the treasure, packaged it up, and delivered it.
Letting an LLM decide its own control flow is the essence of AI autonomy. It's no longer software following an if-then statement rigidly written by a human. If X happens, then do Y. That's traditional programming.
Right.
With an agent, it's software writing its own path, its own logic in real time to solve the user's intent. The human just provides the destination, the agent drives the car.
That is a staggering leap in computational capability.
Yeah.
But I imagine, just like physical drones, not all digital agents are created equal. Depending on the maze you're dropping them into, you might need a small, incredibly fast racing drone, or you might need a slow, heavy-lifting industrial drone. Depending on the task, you need a different kind of agent architecture.
You do. And LangChain provides a whole diagnostic table zoo of agents to help developers choose the right tool for the job.
Let's look at this agent zoo and focus in on the gold standard, the React framework. But first, let's briefly run through the specialized options in the diagnostic table. First, there is tool calling. The primary use case here is triggering specific APIs reliably. This is ideal for OpenAI or Anthropic models, forcing strict JSON object outputs.
Right. Some foundational models are explicitly fine-tuned by their creators to be incredibly good at outputting the exact JSON parameters needed to trigger an external function. If you need a weather API trigger perfectly every single time with the correct latitude and longitude, you use a specialized tool calling agent. It's fast and deterministic.
Next is the XML agent, optimized for legacy systems integration.
This is for the enterprise reality. Not every system is modern. Some older banking or healthcare enterprise systems don't speak modern JSON. They only speak XML. So you need an agent explicitly trained to formulate its thoughts and actions in XML tags to communicate with those legacy servers.
Then there is structured chat, designed for complex tools requiring multiple simultaneous data inputs. And self-ask with search, which I find fascinating. It is designed for iterative fact-finding. It automatically breaks complex multi-layered questions into smaller sequential search queries.
Self-ask is incredible for deep research. Think about what happens if you ask a complex trivia question like, who is the president of the United States when the inventor of the telephone was born? A normal search engine fails at that completely.
Too many variables.
But a self-ask agent knows it can't search that massive concept all at once. It breaks it down using its LLM reasoning. First search, who invented the telephone? Observation, Alexander Graham Bell. Second search, when was Alexander Graham Bell born? Observation, 1847. Third search, who was the U.S. president in 1847? Final answer, James K. Polk. It iteratively walks its way to the truth.
That is amazing. But as cool as self-ask is, the framework highlights one specific agent type in bright red as the absolute pinnacle of current open-ended autonomy, the React framework. Capital R, lower e, capital A, CT, reasoning plus acting. It notes its origin as a groundbreaking 2022 Princeton and Google research paper. It is considered the gold standard for dynamic, multi-step tasks.
Let's deep dive into React. How does this cognitive cycle actually work under the hood?
The React cycle is a brilliant formulation of cognitive architecture. It operates in a continuous, unyielding three-step loop: thought, action, observation.
Let's trace it. Step one, thought. The agent generates an internal reasoning trace outlining a logical step to solve the task.
This is the model literally talking to itself on its scratchpad. It pauses its execution and writes out a sentence explaining its own logic, like, to find this answer, I first need to do this because of X.
Step two, action. The agent selects a specific tool from its toolkit and formats the input required to execute it. Based on its thought, it picks up the tool, maybe it decides it needs the SQL database tool, and it types in the specific query parameters.
Step 3, observation. The agent ingests the result of the tool execution, updates its internal context, and triggers a new thought based on that new information.
It looks at the data the tool returned, writes that data down on its scratchpad, and the loop starts again. Thought, action, observation. Over and over until the goal is met.
Let's walk through a specific scenario to really bring this to life. Let's look at the agent executor in action step by step. Let's imagine a massive corporate logistics scenario.
Let's do it. It highlights the power perfectly.
Step 1, user input. The logistics manager asks the agent a deceptively simple question. What is the status of shipment task Alpha 1?
Simple for a human manager to ask, incredibly complex for a machine to actually find across a global enterprise.
Step 2, initialization. The agent executor wakes up and loads the available tools it has been given by the developer. In this case, it has two tools on its tool belt: status database lookup and search company policy docs.
It's standing in the digital room, looking at its toolkit, evaluating its options.
Step 3, internal thought. The agent deduces, and this is written out internally on the scratchpad, the user is asking for a real-time status update on a specific ID. I need to check the live database for task alpha 1, not the stag policy documents.
It reasoned that out entirely on its own based on the semantic intent of the user's question. It knows status usually relates to a live lookup, not a document search.
Step 4, tool routing. And this is crucial. It dynamically bypasses the search company policy docs tool entirely and fires the status database lookup tool, injecting the input task alpha 1.
It made an autonomous choice. It didn't just blindly fire every tool it had and hope one worked. It intelligently, efficiently routed the flow of execution based on its reasoning.
Step 5, observation. The SQL database runs the query and returns a raw string, status, in progress, delayed at customs.
The tool did its job and handed the real-world data back to the agent's observation window.
Step 6, agent finish. The agent realizes its goal is complete. It writes a final thought. I have the status. It stops the loop, formatting the raw data into natural language, and delivers the final text. The current status of shipment task alpha 1 is in progress, though it is currently delayed at customs.
That is a complete successful React loop. Autonomous problem solving from start to finish.
Okay, I have to ask a highly practical question here, putting myself in the shoes of a developer or a business owner. I'm looking at how much work is happening in the background for a simple question. The model has to generate a thought, format an action, send a network request to an API, wait for the database, read the observation, generate another thought, and formulate an answer. Does this mean React agents are inherently noticeably slower than just asking a regular LLM? If I just ask ChatGPT, it answers instantly. This orchestration process seems like it would take several seconds, maybe longer.
Yes, that is the fundamental trade-off of orchestration. React is slower. It is noticeably, sometimes painfully slower because it pauses to think, to literally generate those internal reasoning traces token by token before it acts. Every thought is a brand new call to the LLM API, which takes time and costs money.
So why use it? Why put up with the latency if it's slower and more expensive?
Because the trade-off is absolute accuracy and autonomy. If you ask a raw, isolated LLM for the real-time status of a specific internal corporate shipment, it will answer instantly, yes.
But it's disconnected.
Right, it will be hallucinating. It will confidently invent a completely fake status out of thin air because it is disconnected from reality. A React agent is slower, but it does not hallucinate. It actively verifies the data in the real world before speaking. In an enterprise environment, a slow, verified, perfectly correct answer is infinitely more valuable than a fast, hallucinated lie that could cost the company millions.
That makes total sense. You are paying a latency tax for absolute, verified truth and the ability to take action. Okay, we've examined all the individual puzzle pieces. We've looked at the foundational brain, the rigid instructions, the RA data ingestion, the memory buffers, and these incredible autonomous reasoning loops. Now, for the grand finale, let's zoom out and watch the entire machine run as one cohesive unit. Let's trace a massive, complex query through the synthesis, the autonomous ecosystem.
This is where we trace the full life cycle of data and user intent through everything we've discussed today. This is the payoff.
Imagine you are the VP of operations at a major company. You open your laptop and type a massive, complex request into your internal LangChain application. You write, cross-reference the new vendor contract we received this morning with our standard compliance policies, check if we have the budget in the Q3 SQL database, and draft a response email to the vendor. Let's trace how LangChain handles this. We start on the left with data ingestion.
Immediately, your document loaders spring into action. They ingest the new vendor PDF and your massive internal compliance manuals. Your text splitters break that data down cleanly using semantic chunking, attaching those vital metadata sticky notes so we don't lose the context of which clause belongs to which policy. The external knowledge is prepped and ready in the vector database.
Then we move to formulation. Your complex human chaos, your typed request, is combined with the specific data chunks the system just retrieved, and they are slammed together inside the chat prompt template. The variables are dynamically filled, the overarching system message persona is applied, and the instruction becomes perfectly clear.
The human intent is now structured machine instruction.
Then, the pipeline takes over. The data moves smoothly through the LCEL, the LangChain expression language. The declarative plumbing routes it from the template directly into the core engine without a hitch.
The data is in motion, flowing toward the brain.
And what is that core engine? It is the cognitive loop, the React agent. It sits at the center, using the LLM as its reasoning engine to spin through cycles of thoughts, actions, and observations. It thinks, first, I need to check compliance. It acts by searching the retrieved chunks. It observes they match. It thinks. Next, I need to check the Q3 budget. It acts by invoking the SQL database tool, writing a custom query. It observes the budget is sufficient. It thinks. Finally, I need to draft the email. It keeps all of these intermediate steps on its scratchpad so it doesn't lose its place in this complex multi-step task.
It is actively solving your operational problem, navigating the corporate maze entirely autonomously.
And finally, delivery. The agent finds the exit. It finishes the task. It hands the raw, victorious answer, the drafted email, and the confirmation of budget and compliance over to the JSON output parser. The parser enforces absolute discipline on the text, strips out any internal conversational fluff from the LLM, and delivers a perfect, machine-readable final application output to your dashboard. We went from an isolated, stateless brain in a jar, a super genius trapped in a windowless room, to a fully functioning digital worker reading databases, verifying legal compliance, checking budgets, and executing real-world tasks.
It really is a breathtaking architecture when you see it all laid out like that end to end. And I think tracing that complex scenario requires us to reflect on that term you just used, digital worker. We are not just talking about scripts anymore. We are talking about autonomous software.
It feels fundamentally different than traditional coding. It feels alive in a way traditional software doesn't.
Because it is fundamentally different. LangChain isn't just a coding library in the way React or Angular are for building static websites. It is a cognitive architecture. AI, by its very nature, is chaotic. It is probabilistic. At its core, it just guesses the next word based on vast statistical probabilities.
Right.
But businesses absolutely hate chaos. Businesses rely on deterministic, reliable, predictable systems. What LangChain does, what this entire orchestration layer achieves, is it standardizes that probabilistic nature into reliable pipelines that businesses can actually trust. It puts necessary guardrails on the raw genius.
It turns theoretical magic into practical engineering.
Exactly. It makes the unpredictable predictable enough to put into production at scale.
Well, we have covered an immense amount of ground today. I want to thank you, the listener, for joining this deep dive into the architecture of modern AI orchestration. We have taken apart the machine and looked at every gear, every spring, and every pipeline. LangChain truly is the invisible bridge making next-generation applications possible. Without orchestration, the smartest AI models in the world are just isolated brains in jars. With it, they have hands, they have memory, and they are actively interacting with the world.
And as we wrap up this deep dive, I want to leave you with a final provocative thought to mull over. Throughout this conversation, we've broken down some very human, very profound concepts into cold, hard mechanics. We define memory not as a lived emotional experience, but as an injected text log, a sophisticated parlor trick of rereading a stenographer's transcript. We define reasoning not as abstract conscious thought, but as a React loop of generating text strings and checking API outputs.
Right, we demystified it completely. We stripped away the magic and exposed the wires.
But here's the question you need to ask yourself as this technology accelerates. As these frameworks become faster, as token context windows grow massive enough to hold years of transcripts, and as these cognitive React loops become completely seamless and instantaneous, at what point does heavily orchestrated software stop feeling like a tool you use and start feeling functionally indistinguishable from a digital colleague you manage?
Oh, wow.
Think about it. If it reasons through problems exactly like you do, remembers your past conversations perfectly, and independently acts to solve your complex operational problems while you sleep, does it really matter if it's just a heavily orchestrated illusion?
That is a wild, slightly unsettling thought to end on. Does the perfect illusion of autonomy eventually just become actual autonomy? We will leave you to ponder that one on your own as you go about your day. Keep questioning the systems, keep looking under the hood, and keep exploring the incredible, rapidly evolving world of autonomous AI. Thanks for diving deep with us.